For 7D, we're going to talk about assessing risk. So we're going to do like what insurance companies and a lot of people do when they look at the empirical probability of things and help them, like how things actually happen in the past, and help them to predict what's going to happen in the future and to help make decisions for the future. But they can also take what happened in smaller populations and say, okay, if that happened here, I can assume we have the same probability for this population here. So we're going to use that to help us kind of make some decisions. So for example, if we're looking at travel risk, we talk about it in like accident rate or death rate. So this would be like the number of deaths per person, the number of accidents per person, or for a certain number of people. So if, say for example, we have 750 accidents per 100,000 people. So rate, we have 750 accidents per means division 100,000 people. So the probability of being an accident is going to be 750 accidents per 100,000 people. So this would end up being accident per person, right? Because that 100,000 gets kind of swallowed up with this. So that means the probability is 0.75%. So out of these 100,000 people, there's a 0.75% chance that someone's going to have an accident. So 0.75% of the total population, or 750, will have an accident. So 750 out of 100,000. So let's say you have a group of 500,000 people. You can assume that this accident rate is going to be the same for this bigger population than it is for the smaller one. So we can take 0.75% or 0.0075 and multiply by that 500,000 to get 3,750. So out of those 500,000 people, you can expect there to be about 3,750 accidents. Okay, now let's look at automobile safety. So here we have 2 years. We have the population in millions for those years. We have the number of fatalities for that year, number of licensed drivers in millions, and the number of vehicle miles driven in trillions. Okay, so we're going to express the two fatality rates and deaths per 100 million vehicle miles traveled. Okay, so first I'm going to figure out the rate for death per mile. So the number of deaths per 1 vehicle mile. Okay, so if I can figure it out for 1, then I can use the same principle we used here to figure it out per 100 million. Okay, so to figure out the number of deaths per mile for 1995, I'm going to take the number of fatalities, or the number of deaths, and divide that by the number of vehicle miles. So this is 2.4 trillion, and trillion is 10 to the 12th. So I do 41,817 divided by, so here again I have multiple things on the bottom, so I'm going to put it in parentheses. So 2.4 times 10 to the 12th. And I get a really, really small number. So if I'm going to put it in scientific notation, I have 1.7 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8. So it's 1.7 times 10 to the negative 8 deaths per mile. Okay, but now I want 100 million vehicle miles. So what I'm going to do is I'm going to take that 1.7 times 10 to the negative 8, I'm going to multiply that by 100 million, which is times 10 to the 6. And I'm going to get actually I'm going to use my answer here and multiply that by 100 times 10 to the 6th. And round it, I have 1.74. So I should expect in 1995 to have 1.74 deaths per 100 million miles. Okay, so 2015, I have the number of deaths. Wait, no, this is a different number. In 2015, there was 35,092 deaths of a total of 3.1 trillion. So I do 35,092 divided by 3.1 times 10 to the 12th. And here I get 1.1. 1, 2, 3, 4, 5, 6, 7, 8. So 1.1 times 10 to the negative 8. So a little bit less. Now to get the 100 million, I take my 1.1 times 10 to the negative 8 and multiply that by 100 million. I'll take this and I'm going to multiply by 100 times 10 to the 6th. I get 1.13. So 2015, I have 1.13 deaths per 100 million miles. So a little bit less. Fairly close, but a little bit less. Okay, part B. Express the 1995 and 2015 fatality rates and deaths per 100,000 population. Okay, so now we want death per population. So for B, if I want death per person, for 1995, I'm going to do number of deaths, that is 41,817 over the total population, which is 263 million. And million is 10 to the 6th. So I have 41,817 divided by 263 times 10 to the 6th. I get 1.59 times 10 to the negative 1, 2, 3, 4. You could write the exact one too if you want to. Okay, so then I'm going to take that 1.59 times 10 to the negative 4th, and I'm going to multiply that by my 100,000. Because I want it per 100,000 population instead of per one person. I'm going to take this and multiply it by 100,000 to get 15.9. So in 1995, you should expect 15.9 deaths, or about 16 deaths per 100,000 people due to traffic fatalities. In 2015, we take my 35,092 and divide by that population, which is 321 million. So 35,092 divided by 32.1, not 32.1, it's just 321 times 10 to the 6th. To get 1.09 times 10 to the 1, 2, 3, 4. So that's per person. So to get per 100,000, I'm going to take my 1.09 times 10 to the negative 4th and multiply that by my 100,000. To get 10.9. So if we're looking at per 100,000 people, you went from 16 down to 11. So 5 fewer fatalities per 100,000 people. Okay, for C, we want the 95 and 2015 fatality rates and deaths per 100,000 licensed drivers. Okay, so this is the total population. Now we're looking at just the drivers. Running out of room here. So if we figure out death per one driver, then for 1995, we have 41,817 over a total of 177 million. So 177 times 10 to the 6th. 41,817 divided by 177 times 10 to the 6th. And we get 2.4 times 10 to the negative 1, 2, 3, 4. And then we're going to multiply that by the 100,000 to get 23.6 deaths per 95. Okay, per 100,000 licensed drivers. If you have 100,000 drivers, you should expect 24 of them to die, which, of course, is going to be less than the population. Okay, so 2015, we have 35,092 deaths per 218 million drivers. So we do 35092 divided by 218 times 10 to the 6th. Oops. And we get 1.6 times 10 to the negative 4. And so 1, 2, 3, 4. And then to get to the 100,000 licensed drivers, we're going to take this 1.6 and multiply that by 100,000. So in 2015, we can expect 16.1 deaths per 100,000 people, or 100,000 licensed drivers. Okay, example 3. Let's look at airplanes. So this shows the number of accidents, fatalities, hours flown, and miles flown for U.S. airlines with scheduled service in selected years. So 2000, 2005, 2010, 2015. Okay, so compute the accident rate per million hours flown in 2000 and 2015. By this measure, has travel on U.S. airlines become safer? Okay, so we're just looking at 2000 and 2015, and we want the accident rate per hours flown. Okay, so note this is per million hours flown, and this is already in millions. So we actually don't have to worry about what we did for the last example where they were in different units, because we already have per million hours. So we want the number of accidents. So in 2000, we had 49 accidents out of a total of 16.7 million hours flown. So we can just do the 49 divided by 16.7 and we get 2.9 accidents per million hours. So it's always handy when you have the same units. Okay, and in 2015, we had 27 accidents out of a total of 17.4 million miles flown. So 27 divided by 17.4 gives me 1.6 accidents per million hours flown. So comparing these, can we conclude that U.S. airlines became safer? Well, yeah, it went from almost 3 accidents per million hours to less than 2 accidents per million hours. So, yeah. Definitely fewer accidents per million hours, so yeah, it looks like it's become safer in the last 15 years. Or between those 15 years. Okay, so now let's look at the accident rate per billion miles flown. So miles flown, so we were looking at hours flown, now we want to look at billion miles flown. And again, these are already in billions of miles flown, so I don't have to worry about doing that extra step that we did in the last example. So in 2000, we had 49 accidents per 7.1 miles flown, billion miles flown, sorry. So 49 divided by 7.1 gives me 6.9 accidents per billion miles flown. And in 2015, we had 27 accidents in 7.6 billion miles. So 27 over 7.6 is 3.6 accidents per billion miles flown. So if we look at this, can we still conclude that the travel on airlines have become safer? Yeah, so we went from 7 accidents per billion miles to less than 4 accidents per billion miles. So this is even a greater case for showing that travel has become safer. Okay, so aside from accidents and death rates, we can also look at vital statistics. So these are going to be your birth rate and your death rate. So again, we can use that to help us make decisions on how things are going. You can also, insurance companies can use these to help them set rates based on, okay, this number of people are expected to get this kind of disease, which is going to cost us this amount of money. And you can also use it to help predict population growth and town growth and see, okay, do I need to build out or do I need to, whatever. You can use it for a lot of different decisions. So example 4, we're going to look at causes of death. So the table shows the leading causes of death in a certain country in a recent year. So in the United States in 2015. The population of the country was 325 million people. So in other words, for heart disease, 614,300 people died out of the total of 325 million in 2015. So if you lived in a typical US city of 500,000, how many people would you expect to die of a stroke in a year? Okay, so first to figure this out, we have to figure out the death rate of a stroke. So we need to know the number of deaths from stroke out of a total population. Right, so anytime we're talking about rates and probabilities, we're talking about like a part out of a whole. So in 2015, one stroke, and we see 133,100 people died from stroke out of a total population of 325 million. So to get the initial death rate, just like we did for example 2, we're going to take this 133,100 and divide by 325 million. And we get 4.1 times 10 to the negative 1, 2, 3, 4. Okay, remember this is death per person. So 4.1 times 10 to the negative for death per person. Okay, so now we can use this general rate to figure out for a specific population. So now we have this 500,000. So we want the number of deaths per 500,000, just like we did for example 2. We're going to take this rate and multiply that by 500,000. Take this times 500,000 to get 204.8. Because they want us to round to the nearest tenth. So that 0.7, so rounds up to 0.8 people for that 500,000 population. So out of 500,000 people, we'd expect almost 205 people to die of stroke. Okay. So again, let's say we live in a typical US city of 500,000. How many people would you expect to die of chronic respiratory diseases? So same chart. This time we're looking at chronic respiratory. So that would be this 147. So the death rate per person, you would have 147,100 from chronic respiratory out of a total of 325 million. So 147 divided by 325. Oops, got my parentheses. 325 times 10 to the 6th And we get 4.5 times 10 to the negative, oh wait, I did 47, 147, so 147, 100. So 147, 100 divided by 3.5 times 10 to the 6th. So we have 4.5 still, which is good, times 10 to the negative 1, 2, 3, 4. Okay, so we have a 4.5 times 10 to the negative 4 deaths per person. We want per 500,000. So out of 500,000 people, I take my 4.5 times 10 to the negative 4, multiply that by 500,000, and I get 226 point, let's see, nearest 10th, so 226.3 people. So out of this 500,000, I expect 226 or 227 people die of chronic respiratory illness or disease. Okay, similar to birth and death rates, we can talk about life expectancy. So overall health at different times in different countries, which compare overall health. So life expectancy is going to be the number of additional years a person of a given age can expect to live, and you can calculate it by studying current death rates. Life expectancy provides a useful measure of overall health, although of course we can't use it to predict individual people's lifespan, right? Because anything can happen. You could die tomorrow of an aneurysm, or you can get hit by a car. You know, there's all sorts of different things that could happen. So this, of course, is just an overall trend. So current age plus your life expectancy would then equal the age you can expect to live to. You know, for our purposes. So example 6. This is another typo here. So use the graph to determine to what age the average 7-year-old could expect to live. Okay, so this is your current age, and this is life expectancy. So if you are 70, your life expectancy is right here, which is about, let's say, like, 13. And so you can expect to live about 13 additional years. So it means the average 70-year-old can expect to live about 13 more years to age 83. So if you're 70 right now, you'll have a life expectancy of 13 years, which means you can expect to live to about 83, barring nothing crazy happening. And similarly, that's a mortality rate, so death rates. So here we have a graph of death rates by age. So this is the death rate per 1,000 people. And we want to estimate the death rate for 50-year-olds. Okay, so this is 50. So the death rate is right about there. So we're going to estimate that is just under this line, which is 2, 4, 6, 10. So this is just under 4. So let's say so each of these are 4. This looks to be about halfway up between the 2 and the 4, so we'll say it's 3. Okay, so this is 3 deaths per 1,000 people. That's what the unit says here. Assuming there's 13.8 million 50-year-olds, how many of this age should be expected to die in a year? Okay, so we say it's 3 deaths per 1,000 people. So we can figure out death per person by taking 3 deaths per 1,000 people. So it's 0.003 death per person. So if we have 13.8 million of them, you take this 0.003 per person, multiply that by 13.8 million. So we have 0.003 times 13.8 times 10 to the 6th. We get 41,400. So of those 13.8 million 50-year-olds, we can expect 41,400 of them to die this year. Just kind of sad. Okay, example 8. Suppose a life insurance company insures 1 million 50-year-old people in a given year. Assume a death rate of 5 per 1,000 people. The cost of the premium is $200 per year, and the death benefit is $50,000. What is the expected profit or loss for the insurance company? Okay, so remember, we're going back to the last section. So expected profit. So we need our events, our probability, and our value. So the events. Well, you have, for insurance company, you always have someone actually buying the policy, right? Probability of that is 100%. Well, then there's the probability that someone is going to live or die. Well, if he lives, life insurance doesn't do anything, so we're not going to consider that because it's not going to affect anything. So the other thing that could happen that would affect anything is that someone dies. Well, so the death rate is 5 per 1,000 people for this age group. So probably is 5 per 1,000. And those are the only things we're going to consider because that's all that can affect this particular situation. Okay, so the value if they sell it to the company is $200. The value if they die, the company is going to lose $50,000. So then I'm going to take the probability times the value. So 1 times 200 plus 5 over 1,000 times negative 50,000. And I add those together and that comes out to be a negative 50. Okay, so remember this is expected value for one policy. So the company can expect to lose on average $50 per policy. Okay, so we have, the life insurance company has 1 million 50-year-olds. So they want to know what is the expected profit for all 1 million. Well, if they expect to lose $50 per million people, or per one person, so negative 50 times 1 million, it's mean negative 50 million. Okay, so they can expect to lose $50 million. Of course, this is a whole number, so we don't really have to round anything. Okay, last example. In 2015, the US population was about 321 million. The overall birth rate was 12.5 births per 1,000 people, and the overall death rate was 8.4 deaths per 1,000 people. So approximately how many births were there in the United States in 2015? Okay, so we have a rate. We have 22.5 births per 1,000 people. And so we can assume that this is going to be the same for populations of all sizes. So we're going to take this rate and we're going to multiply that to the population we actually have. And just confirm, the units do cancel, and we'll look at the number of births, which is what we want. So we do 12.5 divided by 1,000 times 321. Okay. So if I did 12.5 divided by 1,000, and multiply that by 321 times 10 to the 6, I get 4012500. So that is, in 2015, I could expect 4,012,500 births in that year. Okay, well, how many deaths were in the United States in that year? Well, the death rate was 8.4 deaths per 1,000 people. So 8.4 per 1,000 times by 321 million. So now I have 8.4 divided by 1,000 times 321 times 10 to the 6th. And I get 2,696,400. So that's 2,696,400. Okay, so based on births and deaths alone, so we're not including immigration here, about how much the US population increased during 2015. Okay, so the population, so all the births increased, right? So you have the population that increased by 4,012,500. And then it decreased by all the deaths. So we find number in, number out, we can say how much the population changed. So I do this minus this, put it in the calculator, and I get 1,316,100 people. So the population increased by a little over 1 million people. Okay, so suppose during 2015 the US population actually increased by 3 million. Based on this fact and the results from C, estimate how many people immigrated to the United States. So assuming that the only people, it was either birth, death, or immigration. So this is how we increased by births and deaths. This was total. So total was 3 million with births, deaths, and immigration. This is just birth, deaths. So the difference between those would have to be just the immigration. So I subtract the 1 million from that. And I get 1,683,900. So there's 1,683,900 immigrants. So we grew more from immigrants than we did from natural birth and selection and death. So if we want the proportion of the overall population growth due to immigration, and we can see that this was more than that, so it should be greater than 50%. We want the actual proportion. So of the overall population growth, so that's my whole. So overall population growth was the 3 million. And the part was the immigration, so that would be 1,683,900. So I do the part over the whole, and I end up with a 0.5613. And if I put that as a percentage, it would be 56.13%. So 56% of the overall growth was due to immigration. And that is 7.4.